want to talk about Eulerian tours today. This is a pretty easy concept. We could have started with something like this earlier. We often do in a class, but yeah, it doesn't matter. Okay, so we're going to talk about walks and closed walks in particular. So remember, a walk is just a sequence of edges and vertices such that you have the edges are adjacent to the two vertices on either side. So like a walk W usually looks something like V0, E1, V1, E2, V2, and so on and so forth. And you end with like let's say end with EL minus 1, VL. Okay. And so the edges, these intermediate edges are composed precisely of the two vertices on the ends there. It's just a sequence of edges and vertices that you have the appropriate adjacencies. And you're allowed to repeat edges, you're allowed to repeat vertices. It's just a sequence in the graph there. Okay. I'm not going to redefine it here, but so walk is closed. And I think we actually used this definition last time, maybe we've used it before, but a walk's closed simply if V0 equals VL. So if you have the same vertex at the start and finish. So if V0 equals VL. There may be further repeats of V0 and VL in the sequence, but as long as the start and end are the same, then it's closed. And it's actually worth noting. So, if you have a closed walk, I mean, this will come up in a little bit later. Let's say it does repeat some. So you have a closed walk, looks something like this. Then like the start and finish is arbitrary now. Like I could start here and just traverse through and end here, or I could start here, traverse through and end there, anything like that. So once it's closed, much like when you have a cycle, there's sort of anywhere can be your start and finish. And this will be handy here, okay? But what we really want is what's called an Eulerian tour. So an Eulerian, or I'll just call it an Euler tour. This is often called an Euler circuit. Often the term circuit is used for closed walk. I haven't been using that term. Sometimes we call them an Eulerian tour or an Eulerian circuit. We'll use Euler tour in these notes here. Is a closed walk that uses every edge of the graph exactly once. Uses every edge of the graph exactly once. Okay, so each edge is visited, but not again. So just one time exactly. And some graphs have Eulerian walks and some don't, or sorry, Eulerian tours and some don't. Let me just give two examples here real quick. Oh yeah, and it's very, I don't know if very worthwhile, but what we'll talk about today applies perfectly well for multigraphs. So I'll state the theorems with the term multigraph in them. It actually makes them a little bit easier. But let's even have our example with a multigraph here. So say this is our graph here. So we've got this double edge here and these 5 vertices, and it's not too hard to find an Eulerian walk. There's not many different ways to label it here. I'll label the vertices, and we just have to confirm that there are edges between them that haven't been used. So say we start there, go here 2, and then it's not that hard to find, but 2, 3, say 4, and then back down here to 5, 6, 7, and then back here to 8. Okay, so it travels along this edge. You can even direct them sometimes to make it easier to illustrate. So it goes then 2 to 3, 3 to 4, then back down to here to 5, then out to 6, then here to 7, then here to 8. Okay, so it's closed. The start and end equal each other, and you notice each edge was used exactly one time. Okay, so that is one. And here's an example that doesn't have one. Oops. Let's say like this, and then let's add, these are both multi-edges. This is just one vertex here. Okay. So this one has no Eulerian tour. Okay. And this is actually a famous specific example. This is a model of the bridges in the city of Königsberg. It's now called Kaliningrad. It's part of Russia now. And the Euler was asked, or this was the question of the day, was like, if these represented bridges in a city, and the question was, can I walk along all the bridges and make a nice tour and walk along each bridge exactly once and return to where I started, right? A natural thing to wonder. And it turns out it was impossible, and Euler was able to show that and showed more generally when it might be possible and not possible in a graph. And this one's, so I'm going to say no Eulerian tour. And let's try and figure out why this one at least doesn't have one. By examination, it doesn't take too long to figure it out. Many of you maybe already see it. But suppose it did have an Eulerian tour, then it has this closed walk that starts and ends in the same vertex that uses every edge. So I can just pretend for a moment that my starting point, it's best maybe to start on this vertex here. So if I had one, I can start here, travel through everything, and return here, right? But if you think about this vertex, the degree here is going to be a problem, right? Because if this vertex is in my tour, like I leave, it's not symmetric, but let's just say for a second, I left from this edge here, and then I have to use up these two edges. So like later on, I have to re-enter this guy here. And then this edge still hasn't been used, so I have to leave. And now there's no returning to this vertex anymore. I started here, I have to end here, but I went out, in, out. Like, how can I end here? I can't, right? This degree 3 was like a problem for me here. If you start somewhere else and try and do the same, you'll run into similar issues. Actually, all the vertices here are odd. But it turns out the existence of a single odd vertex causes you issues. And actually, you can kind of see that, and it's almost like a proof by example. If you think, again, suppose I have one odd degree vertex and I have an Eulerian tour, then I can pretend I start there because it's closed. I leave, enter, leave, enter, leave, enter, leave, enter. If I want to end by entering there, which I have to, that means you have an even number. For every out, you have an in. That's actually the proof. Let me write this down, be a little more formal. But that's a proof of one direction. That says you can't have odd degree vertices. What's interesting is that that's sufficient. Having no odd degree vertices is the only impediment, obviously except for connectivity, for whether or not you have an Eulerian tour. Okay, so that's the Eulerian tour theorem. I guess this was actually due to Euler. So this says a connected, right? We'll always assume our graphs are connected in these examples, otherwise there's no tour, right? You can't get across if there's no edge. So connected multigraph. Usually put multi in parentheses, doesn't matter. We didn't say anything about loops, but obviously loops have no real influence on a Euler tour or not, right? If you reach a vertex and there's a loop, you can always travel along the loop, thus using up the loop, and it's not going to cause you to get trapped or anything like that. So we won't do any examples with loops because they don't cause any issues. But having multi-edges, like whether, that can change things dramatically, right? I mean, just as a very, very simple example, for instance, this graph has no Euler tour, right? I mean, you start here, you end there, and that's it. But this one, maybe, okay, let's keep them the same. That one doesn't, but that does. That has an Euler tour, right? So multi-edges do have an influence here, but loops aren't going to change anything, right? Adding this loop here isn't going to magically give me an Euler tour, and over here, it's not going to take away the existence of an Euler tour either. Okay, all right, so connected multigraph, G, has an Euler tour if and only if all the degrees are even, okay? If and only if all, what did I write there? Oh, yeah, okay. Every vertex of G has even degree, okay? We saw here the existence of an odd degree caused us to not be able to have an Euler tour, but what's more interesting is the reverse direction. Okay, so we actually basically already proved this one here, but in an Euler tour, so suppose we have an Euler tour and we walk along it. So walk visits, then leaves a vertex, right? And so the degrees have to be even. Anytime you have a vertex, you have an edge in and then you have an edge out. And actually, in fact, in this way, illustrating this with directed edges make it a lot easier to visualize what's going on, right? You have an in and then you have an out. So if you orient the edges according to the direction you took along your walk, every vertex will have as many in edges as it has out edges. So degrees are even. Okay. This relies very much on closedness as well. Although there is something that called an Euler trail that doesn't require you to be closed. You just start and end at the same point. We'll talk about that in a little bit. Actually, I think that's a simple homework exercise. So the reverse direction is more interesting. Suppose all degrees are even. How do we actually confirm that we do have one of these nice closed walks that use every edge? Okay, so suppose G has all degrees even. Okay. All. And we want to find an Euler tour. It's connected as well, right? That was part of the assumption there. Okay, so in a lot of these examples, when we've tried to find what's a good maybe I don't need an analogy for this one. We're going to take a longest walk that we have in our thing. Typical strategy, if that walk is both closed and uses all the edges, then we're done. So we'll suppose that either of those two things fail and try to rule them out. Okay. So we have all degrees are even, and let's let W, and this one's a lot easier to prove with a picture. I mean, all of them will be today, but let's let this be a longest walk. So we start V0, E1, V1, E2, V2, so on and so forth, EL minus 1, VL. Okay. So this is the walk, I guess, of length L minus 1, right? We have L minus 1 edges in the thing here. Be a longest walk in G. I don't know where it starts. I don't know where it ends. I just know it's a longest. There's finitely many. Oh, yeah, sorry. Okay, I need to amend this. What I've written here is nonsense, actually. Can someone tell me? This is a good little sanity check here. Is there such thing as a longest walk? I need to add something important here. Longest walk without repeated edges, right? Walks can repeat edges. So longest walk could just go back and forth forever along a single edge. Like as long as you have an edge, there's no longest walk formally by that definition. So I want a longest walk in G with no repeated edges. Okay. It's not necessarily a path because the vertices can be repeated certainly in a walk, but I have no repeated edges. And that's sensible because I'm trying to create an Euler tour which has no repeated edges. So this is like my the first attempt. Just start somewhere, start walking, and go as long as you can without repeating. I mean, that doesn't necessarily produce you a longest one, but one does exist because there's finitely many. Okay, that's maybe worth stating. There's finitely many walks with no repeated edges, obviously. There's finitely many edges. So among all of those, there's at least one that's longest. Okay, so now the first thing I want to do is examine VL. Examine the end there, okay? I'm going to illustrate this and then just say in words what's going on. What I want to confirm is actually that VL equals V naught, and that'll follow from the even degree property here. So it turns out that a longest walk with no repeated edges in a graph with all degrees even will necessarily be closed. It doesn't necessarily use every edge, but it has to be closed. So let's examine VL. Okay, so here's VL, and VL has some incident edges, right? I've drawn 4, but I mean, we don't, actually, no, okay, this is an example again. It has even degree, so it has 2, 4, 6, 8, something like that. Now, VL is the end, right? It's the end of the walk. So it means at some point, I go in and stop at VL, okay? But there's no unused edge incident to VL. Otherwise, I could extend my walk, right? If any one of these edges had not been walked across yet, then I could have extended this walk. Now, any prior visit to VL necessarily had an exit as well. So say this was a previous entrance, then I exited somehow as well, right? And so let me add a couple more edges just to illustrate. 1, 2, 3, 4, 5, 6. Okay, definitely I don't want 7. Let me just get rid of that last one. So any prior visits had a way of getting out because we ended up in VL. This was like I can even label these. This edge was EL minus 1. I don't know what edges these were. There were some E sub i's for different values, i's here. But notice each of these prior visits eat up 2 of the incident edges, right? In, out, in, out, in, out. And we end with an in to VL, but because the degree is even, there's this unused edge here. And so at the moment it seems, oh, well then I can actually escape there, but I shouldn't be able to escape there. That edge should have been used. What's the only way in which this edge could have been used prior to me visiting there? It'd be if I literally started in VL, the whole thing, and walked out. The first step I made was walk out, and then in, out, and then in at the very end. That's the only way. So only way to use this edge, because of the evenness, was to start with it. And what does that mean? That means this implies that VL equals V0, that the starting point was actually the ending point there, okay? And very much so this used that it was even. If the degree was odd, then ending in VL wouldn't have been a problem. With, you know, we could have, we ended here and all prior visits went in and out, went in and out, in and out, and didn't leave a leftover edge, okay? All right, so this means actually that our longest walk without a repeated edge is actually closed. So W is closed. Well, that's good, but that still doesn't solve the problem, right? If W uses each edge of G, then we're done, right? That's what we're looking for. We're looking for a walk that is closed and uses every edge of G. If it does that, then we're done. So otherwise, there exists an edge, E, which can be written as UVI, incident, so to W at vertex VI. And let me draw this. And we've seen this many times before, right? So here's my walk. Again, I didn't, when I illustrate these, I usually don't repeat edges just because it's hard to draw, but like certainly edges. Oh, no, there's no repeated edges actually, right? This walk had that property that there were no repeated edges. There could be repeated vertices, so it might look like this, but it's not so bad to draw. Okay, so this is my walk. If it happens to use up every edge, I'm done. So suppose there's an edge which it doesn't use. Because the graph is connected, there is an edge that looks like this, that's incident to it in this way here. Or it's possible that the unused edge goes between two vertices on the walk. That's certainly possible, right? This walk might actually use every vertex. But you'll see that these two examples are not different from each other. So we've got a walk, and there exists this edge, E, which looks like U, which is potentially on the walk, potentially not, but crucially VI, which is on the walk. And remember, I named the walk, it has vertices V0, V1, V2, V3, V4. So VI is just one of those, like somewhere in the middle of the walk, this guy's used here, okay? But like, I'll label this one too at the same time. This could be VI, U as well. Although here you had two choices. It could have done, you know, VI up here and U down here, or it doesn't matter. But it actually won't make a difference. In a longest path or situation, it mattered that it went off here, but we're not looking for a path, so it doesn't matter. Okay. Anybody see a contradiction in this picture? There's a longer path here, clearly a longer path. It's maybe easier to see here, but just do this. Walk along from here and then follow the walk from this point either direction, right? It's a closed walk, so I can go here and like go along like this, go up here, go down here. I don't know which way this one went. Actually, I have choices, go here and then end there. So okay. I'm going to write this, but this is not the way it's put in the notes, but I'm going to write E plus W forms a longer walk, okay? Now, W started from V0, so I'm not actually adding E to the beginning of V0, I'm adding it somewhere in the middle, but because this is a closed walk, I can choose any starting and ending I wanted, right? We discussed that a little bit earlier. So this is a longer walk. Now, maybe there's something bugging you here a little bit, right? What's not true about this walk, at least by the illustration? It's not closed, but does that actually matter? Did we assume that W was closed? No, we didn't assume it, we proved it, right? So W was the longest walk that didn't repeat edges, and it turns out it's closed. Bonus. Now we found if we don't use every edge and there's an edge going off the walk, we can add that to the walk to get a longer walk. That's a contradiction to the longest walk property. It'll turn out that that longer walk, if it exists, has to be closed as well. But I mean, that doesn't matter, right? Like we got a contradiction by finding a longer walk, okay? Does everybody see that this edge here wouldn't have caused any problem either, right? It still would have been a longer walk as well. It just, would have reused two vertices that were already on our walk, but reusing vertices is fine. Like we could have started here, gone there, and then traveled all around and started in where you want. So you can be a little more formal with the actual resulting walk. It's something like, it's, you start in U, and then you go to E, and then you go to VI, and then you go to EI plus 1, right? The next edge on the original walk, and then that goes to VI plus 1. But you have to be careful because maybe it just so happened that VI was VL, and so the next VI plus 1 is V naught. So like there's, I don't know, like a modulo index, whatever, but this goes on and then eventually reaches VL, and which equals V0, right? So I'll put in equals V0. And then that continues to E1, and then this thing continues until we reach I'm lost here, VI plus 1. No, VI minus 1. The vertex before this vertex on the thing. Remember, it's not, this one's, the new walk's not closed, okay? Anyway, you can look in the notes for a more precise statement, but it was clear we could just add this edge on, get a longer walk, and it's a contradiction. So a longest walk that doesn't repeat edges necessarily uses every single edge of the graph. Otherwise, we get a contradiction. So yeah, that's an Euler tour, okay? We didn't actually find it, right? This is non-constructive. We'll give a constructive proof in a moment, okay? So an Euler tour exists. Okay, and that's the end of the proof, right? We had all degrees even. Actually, the only place we used all degrees even was here in establishing that the thing was closed. That was important. Okay, let me give another characterization. This characterization that you have an Euler tour if and only if all degrees are even and you're connected is very, very well known. We'll see it will come up a couple times in the class, but this is definitely, it's not a hard theorem at all, as we saw, but it's very widely known. The next characterization is less well known. And then actually next week, I'll give you one that's completely unknown, but like really cool and different. Okay, so a connected multigraph, G has an Euler tour if and only if G is the edge disjoint union of cycles. Okay, I'll give an example here in a moment. That's the same as saying G has a cycle decomposition. Okay, if you've been reading some of the open problems, and maybe there was an exercise of this type in the notes, this stuff has been defined here. But let me just explain what a cycle decomposition is. Well, it means your graph is an edge disjoint union of cycles. So it means that you can break the graph into a bunch of cycles, and those cycles compose all the edges of the graph. So every edge appears in exactly one of these cycles, okay? So you can partition the edge set into cycles. That's what it means, right? Partition are sets of edges that don't share any between each other. So it's a decomposition, right? It breaks the edges up into those. Vertices will be repeated a bit among the cycles, of course, but the edges are not repeated. So like maybe a really simple example, these are usually good to do in like color. So let's take like K5, for example, here. So K5 has this really simple cycle decomposition. I can decompose it in the following 5 cycles. Right? That 5 cycle and this 5 cycle. Right? Those 2 cycles use up all the edges of the graph, and they're disjoint from each other, and there's 2 of them there, okay? The cycles don't necessarily have to use up every vertex of the graph, though. Like that's, let me modify this graph here, maybe add one more example. Let's say we had an additional vertex out here, and then we also had a multi-edge here. So there's 2 edges here. So this is not a K5 anymore, but this 6 vertex graph with like all edges here, and then these 3 additional edges here, this is a cycle decomposition of this. And this is a multi-graph. These are 2 edges. I'm not using that edge twice. It's 2 different edges, okay? So that's a cycle decomposition of this 6 vertex graph into 3 cycles, okay? So one actually question in general is for various types of graphs, like what can I decompose them into? There are many open problems in graph theory of that type. Can I decompose complete graphs into trees, for instance? There are a bunch of different examples like that. If you read through the conjectures and open problems in the notes, a number of those refer to this type of stuff. It's easy to build graphs that are decompositions of certain things by just laying those copies of graphs down in such a way that like produces something. But given a graph, the reverse directions in general very hard. Okay, so, but the theorem here says if I can decompose into cycles, then I have an Euler tour and vice versa. Now, this characterization, it's possible to prove this without using the previous theorem, but I'm going to use the previous theorem. Okay, so we're going to use the even degreeness to get this. And then it's like, this is really like, I would even call this a corollary then, because it follows quite easily. Okay, all right, good. So let's prove this guy here. So we have two directions again. So let's go reverse as the first direction. Let's say that we have a cycle decomposition, and let's confirm that we have an Euler tour, okay? So you can build the Euler tour off from the cycle decomposition directly, but let's use the previous theorem, and then maybe we'll talk about that. Okay, so say G has a cycle decomposition. Okay, and I just want to prove that the result that G has all degrees even. If it has all degrees, G is connected always, right? So G is always connected. So if it has a cycle decomposition, why are all the degrees even? Well, I like to see it in this procedural way here. Let's place down all the vertices of the graph with no edges yet. And the cycle decomposition just corresponds to drawing down one by one the cycles that are in the decomposition. So just build up G by adding down the cycles, right? So say it's got a cycle decomposition, C1, C2, up to CK. So these disjoint cycles together make up all the edges of the graph. So just draw them down. Here's cycle 1, added there. Here's cycle 2. Right? Maybe cycle 3 is like, it is here, and these are repeated edges, and so on and so forth, right? So just keep drawing down the cycles. But each time I add, adding cycles to the empty graph. Here, when I say empty graph, I mean the graph on the same vertices, but no edges. So each time I add a cycle, what does it do to the degrees of the graph here? It increases degrees. Yeah, exactly, Eric. It keeps them even, and even more precisely, although your conclusion is all we need. It increases degrees by 0 or 2, right? Each vertex either goes up by 2 because it was in the cycle, or goes up by 0 because it didn't have anything to do with the cycle. But the result is when I finish this procedure, all the degrees will be even. Okay, then all degrees even, and then there exists an Euler tour by the previous theorem, right? And again, the result at the end is connected because we're given G is connected in the first place. Just laying down these cycles doesn't necessarily connect you unless you knew that in advance. Now, I don't want to prove it, but if you think about this for a little bit, you can make this procedure find the Euler tour directly without invoking the even degree theorem. And the rough idea is place down the first cycle, which clearly has an Euler tour. Just walk around the cycle. Now place down the second cycle. That cycle also has a tour just around it. If it shares vertices with this guy, then it's easy to append the two to each other, right? Walk along this one, and then from the shared vertex, walk along the other one. If they're not shared, then just keep both in mind, and eventually they'll get appended, right? Or maybe a better way is to lay down these cycles in such a way that at each step you're connected, right? So lay down a cycle, then the next cycle, make sure it's sharing some vertices with the previous cycle. Then the next one, make sure it's sharing some vertices with the previous thing, and just keep, adding these cycles on, these loops, and that'll be your Euler tour at the end there too. So we don't need to invoke the previous theorem, but we did. Okay, so the other direction is, well, just as easy. So G has an Euler tour. Okay, so then by previous theorem, all degrees of G are even. Okay, so all the degrees are even here, and it's connected. And say I wanted to find a cycle decomposition. What would be the naive way of starting this approach? And actually, you don't even need connectivity here. All the degrees are even. What should I do? In fact, you guys know something here based on one of the exam questions, right? The one with the regular graphs. I mean, it's not quite it here, but yeah, exactly. Van says, start a walk and remove edges as you go. In fact, so so then we want to be careful here, right? So we have an Euler tour, but we want to produce a cycle decomposition. So I want to create cycles. So I'll start a walk somewhere, and let's not remove edges yet, but let's walk. And what do I want to do with this walk? What's my goal at this point? What am I trying to create? Yeah, I'm trying to get cycles, right? So I don't want to repeat anything. So I just want to keep walking. But because all degrees are even, I will eventually return to where I started here without repeating, thus creating a cycle, right? So I can just walk and find a cycle. So walk to create a cycle. This uses the even degree property. I find a cycle, remove that cycle. Remove the cycle. When I say remove the cycle, I mean remove the edges of the cycle, not the vertices. So edges of the cycle. Okay. After I remove the edges of that cycle, what am I left with? I'm left with a graph whose degrees are clearly still all even. Maybe not connected, but it actually doesn't matter if I'm not connected, right? If I'm not connected, all my degrees are even, I can still start the procedure again. Start at a vertex whose degree is not 0 and walk. I eventually have to return to where I started because of the even degree property. And so I'll find another cycle, remove that, and just repeat this procedure until you've removed every edge of the graph. At each step, all the degrees are even, so you can find a cycle, or all degrees are 0, in which case you're done. Okay? And each of the cycles produced are obviously edge disjoint because I removed the edges after finding the cycle, so you can never repeat an edge. And that finds my edge decomposition. I mean, my cycle decomposition, okay? Remove the cycle, and I'm just saying, and repeat. It's easier to describe it this way than to draw everything. Remove a cycle, remove a cycle, remove a cycle, remove a cycle. This gives a cycle decomposition. Okay, so we don't even need connectivity actually in this case to get this started. If all the degrees of your graph are even, you will have a cycle decomposition anyway. That's like a stronger statement that we can make. Okay, this one though is a little bit harder to use directly. The Euler tour, although it's not impossible, you have to look at your Euler tour and break it up into cycles and then take those off one at a time. And that's certainly possible to do. I think an inductive argument will allow you to do that. It's just, if you want to do it that way, you have to maintain the connectivity property at each step. And so you can't just remove any cycle you want. You have to carefully choose an appropriate cycle to remove. You have to prove that there's a cycle in the Euler tour that can be removed that won't disconnect the graph, except for possibly creating vertices of degree 0, which you'll throw away. Okay, so it's a little bit more technical. But anyway, our result here was to use the previous. Okay, so yeah, we should have enough time here. We've given 2 characterizations, but we haven't actually shown how to find an Euler tour. So I want to describe an incredibly simple algorithm, which will actually produce for you an Euler tour, and hopefully we have enough time to prove that it works as well. Okay, so this is going to be an algorithm for actually finding an Euler tour. Okay, so this is Fleury's algorithm. Okay, and you can run this on any graph, whether it has an Euler tour or not. If it has an Euler tour, it will find it. If it doesn't have an Euler tour, it'll terminate without finding it. You'll run into a trapped situation here. But just to make describing it easier and proving the things here, I'm going to suppose that G has an Euler tour. Okay. Now, it's not surprising that there exists a simple algorithm for finding a Euler tour, because at least the first characterization theorem is very easy to run. I mean, to confirm by compute, like it's clearly not NP complete, right? If like I give you a graph and say, does it have an Euler tour? All your computer has to check is, are all the degrees even? That's an easy check for a graph, right? Okay, so one question is like, how do you encode a graph? You can put it in an adjacency matrix. Actually, we didn't talk concretely about this. Maybe I briefly mentioned it, but you can record all the vertices degrees or all the incidences in a matrix, and then you just check entries of a matrix, and like that's fast, right? So you can check if they're even, and then you know that you don't find it, but you know it exists. Okay. So anyway, all right. So I'm just gonna put in parentheses. So let G be a graph with an Euler tour, but you can certainly run this on a graph without one. But just to make the proof clearer, we'll assume that it has one and just see that it actually produces one. Okay. So the algorithm, we start with an arbitrary vertex V in the vertex set of G, and we just start walking, okay? And what are we gonna do? So we produce a walk from V, well, just by traversing edges, almost arbitrarily. We just have to keep one thing, okay? So let's say as follows. So what I'm going to do is each time I walk across an edge, I'm going to delete that edge from the graph because I never want to walk along it again. So I don't ever want it to be available to me. Okay, so after traversing an edge, remove it. Okay, just the edge. If removing that edge creates a vertex of degree 0, so when I walk out of a vertex, it sort of isolates that vertex from the rest of the graph, I'm also going to remove that vertex. Okay, so like, you know, imagine I'm at a vertex here. I enter that vertex and then remove that edge, and then I walk out of that vertex and remove that edge, and now this vertex is by itself. I'm going to remove this as well because I don't need to worry about that anymore, right? All the edges on that guy have been used up. I don't need to like, keep track of, oh, I need to use it. Like there's nothing left there. Okay, so and remove isolated vertex if created. Okay, so after I remove that edge, if it isolates a vertex, I mean, makes it degree 0, throw it away as well, just so that the algorithm can work nicely. And the only thing I have to take care of is at each step, walk along an edge. Okay, so we're walking. So when I'm at a vertex, I only have access to the edges that are incident to that vertex, right? It's a walk. But the only thing I want to avoid is I examine all these edges and check if one of them is a non-bridge, then walk on that. Okay, always take a non-bridge in the graph that you have so far. You want to avoid bridges, okay? That is not a bridge, if possible. Okay, sometimes you have no choice. Sometimes the edge might be a bridge and then you have to walk across it, okay? If, how did I say this? If, yeah, always walk along an edge that is not a bridge if one is available at the current vertex. Okay, that's the entire algorithm. Start at a vertex, start walking, delete things that you walked over, and never walk along a bridge if you can avoid it. Okay, let me run it on an example here. That'll make it a lot easier to see. So, sorry, couldn't mute in time. Right. This one's a little complicated because I want to make sure I create some bridges along the way so we can see that there are actually opportunities to make a choice. Okay. So this should be my graph. Yeah, let me add another edge here so that actually, okay, all degrees are even, I hope. 1, 2, 3, 4, 1, 2, 3, 4, 4. Yeah, it looks like it's even 4 regular, okay? So it does have an Euler tour. Let's actually find one using Fleury's algorithm. Let's start here. This is my vertex V, and let's travel along this edge. That's my first edge. And then I travel along this edge as my second. Okay, yeah. So I mean, I should actually like state what I'm doing here, right? We should use the algorithm. Algorithm says traverse an edge as long as it's not a bridge. If I look at all these edges, removing any one of them will not disconnect the graph. That just takes some examination. Actually, in implementing this algorithm, you do have to do a little bit of work in deciding when is a vertex, an edge, a bridge or not. Like that might take a little bit of work. It's not that hard though, as we'll see when we get into the proof. So I can take any one. I'm going to take this one here. Okay. This edge is not a bridge either, right? So we'll take this one here. It'll be easier when we see an edge that is a bridge, then it becomes clear. And then let's walk around along 3 here. Okay. Now it's not relevant to us yet, but notice this edge here now, this is definitely a bridge, right? This edge, if I remove it from the existing graph, would disconnect this vertex from everything else. Now, it doesn't matter to me yet because I'm not adjacent to this edge. I don't have the opportunity to take it, but it is a bridge, okay? This vertex doesn't get removed until that edge is removed, okay? All right, so I take 3, and then let's take 4, and then let's take 5, And now we get something finally interesting. So we're here. I could take this edge or this edge or this edge, but this edge here, as we noticed, is a bridge. And so now we see why it's relevant to avoid a bridge. If I were to take this bridge edge, I would end up here and be stuck because I've already used all the incident edges here. It'll turn out in this procedure, the only time you have a bridge is when you have a vertex of degree 1 on one end. And that's the only bridges. But in general, that's not true, right? We have graphs with bridges, a bigger thing, but this procedure won't allow that to happen. That's part of the proof, but okay. So the point is, at this point here, this edge, we can't use it. Okay, but we have to use it somehow later, so it'll come up. But let's continue. So we can't use that one. We could use this one, go 6, and then go down 7. And now we have another interesting situation here. This edge is a bridge, right? And actually so, okay, what did I say here? Yeah, okay, so the bridge, yeah, I misspoke. There can be bridges whose degrees are higher than 1 on both ends, but when we use them, it'll be only when they have a degree 1 on both sides, because this edge is a bridge, but actually its end vertex is degree 2 here, and this one at the moment is degree 3. But it's still a bridge, because if I remove this edge, keep in mind the red edges are gone, then this vertex and this vertex, they form a component, but this vertex, and the remaining vertices also form a component that could only be reached across this edge here. Maybe it'd be better to like erase the edges as I draw them, right? Red means it's not there, it's a little hard to see. Right? So it means I can't travel along this edge yet. I'm here now. And then from here, this edge, neither of these edges are bridges. Again, it takes a little confirmation, but let's say I go this way, 8, then up 9, then down 10. And now I'm here, and the algorithm said don't use a bridge if possible. Right? This edge is a bridge, but I have no choice. So you take the bridge edge. Now that's fortunate because that's not a problem. That is a bridge and I deleted, thus disconnecting the graph. But remember, the vertex also gets deleted at the same time because this vertex now has degree 0. It gets deleted. And then same issue. It's a bridge, but it's okay because that bridge actually ends the thing. And it actually ends me back where I started. That's 12, okay? So you can see we actually did produce an Euler tour, but maybe we just got lucky, right? We have to prove that this thing works here, okay? But that's it. Start a vertex, walk. Don't walk along bridges unless you're forced to. Basically, all we need to do in the proof is confirm that you never run into a situation that looks like this, where both of these edges are bridges. If you only ever look like this, like when I reach here and I need to walk and there's only one edge and it's a bridge, then it's okay. It's safe to walk along bridges if I'm going to delete the edge and the vertex. If you remember, that's something we learned about connectivity very, very early on, right? When you remove this vertex that might disconnect the graph into 2 components, it actually doesn't count if the vertex itself is disappearing. Okay, it's a similar idea here. Right? So, okay, this. I'm not sure I'm going to be able to finish this in time, so let me try and sketch it here. Okay, well, proof. What's the theorem, actually? The theorem is that it works. Yeah, right. The Fleury's algorithm produces an Euler tour. That's the theorem. Okay. Yeah, you know what? Let's just call it a day instead. There's 2 options here. I can keep you late, or I can rush the proof. Neither of which is particularly desirable. So, but I do want to tell this. So maybe next time. Yeah, we're going to be talking about Euler tours and stuff for a couple lectures. So we can just do this next time. You can read ahead if you like to. It's not that hard, but it's a cute little algorithm. So.